Hello, this is Lavneet from Clomotech. This is the second video in our series of videos related to topics in C programming and data structures. Today we are going to talk about linked lists. Well, the implementation that we generally do during our learning about linked list is pretty simple, and we are going to do that in a pre-baked fashion. It is already done and I will show you that. But we will go little bit beyond that, beyond simple implementation, and try to address some issues which come in real world scenarios. And how do we manage the objects in C using this data structure of linked lists. Linked list in general consists of nodes connected to each other as is shown in this graphic on the screen. It consists of a node which has two parts. The left part that I show here in a node, this contains the information that is required by user during the course of the program execution. And then it contains the second part, which is pointer to the next node. So each node contains the pointer to the next node. So therefore, that is how it is linked to each other. The nodes are linked to each other, and therefore it is called linked lists. This is one implementation of linked list data structure using pointers. There is another one using arrays, but we are not going to talk about that. It is the most used one is using pointers. In our case, what are we going to do is we are keeping the first node of our linked list as a special node. We call it head node. We'll have a dedicated pointer to this node present in our program. A dedicated pointer will be there, and this node's information part will contain the count of the nodes in the remaining of the linked list. So for example, in this list, there are three nodes which are actually useful for the user to store the data. So the count of the nodes should be 3 in the head nodes information part. And that's, I think, pretty much it. Another thing is that the last node of the linked list will contain a pointer to null, null pointer basically pointing to nothing. So that will indicate the end of the list. So this pointer will be a null pointer. All right. So what I have done actually is I have gone ahead and implemented a linked list. So this is my structure which will represent which represents the node of the linked list that we talked about. It has got the information part, which is an integer to begin with, and it is also having a next pointer which is pointing to the list, the node next to it. So the type of the node that it is pointing to is again the node s type. So therefore the type of this pointer is node s star, the pointer to the same type of node. So that is pretty easy to understand actually. And then we just type def it so that we don't need to write everywhere struct node s. So we just type def struct node s to node. We have some typical operations of linked list. So insert at front will insert this information into the front of the list. Insert at the end will have this information inserted into the last of the list. And insert after is to insert this information after the information after the node that contains the information in this variable called after. So we'll see the usage of this. Similarly, insert before will insert the information in this info field into a new node created before a node which contains the information with variable name before. Similarly, we have some delete operations. Delete will do is deletion of a single node with this information, and delete will actually delete the whole list. We also give function to use to get the count of the nodes, and then given an index like first 1 2 3 0 1 2 3 and so on, we can get the information that is contained in the ith node, and then we can also find the node with this information whether it exists in the list or not, and return 1 or 0. 1 means it exists, 0 means it does not exist, or true or false if we use type diffs. So this is our kind of an interface of our linked list data structure. And what I have done is I have created a library project, C++ console, sorry, C++ library project. And this library project is what we are going to use for having our data structures. So what I am imagining is that this is the library that we are building, and it contains implementation of our data structures. It will be shipped in a binary form with the header files that we want to ship, so that our user can use this library for their usage. So in our case here, for the training purpose, we have dslib training executable. This is an executable that references the dslib. Here it is referencing it by project, but if we had these two things in different solution, it could very well refer it as a library as well. So let me repeat. So the library we are going to ship will be the binary file that contains the implementation as well as the header file. So we will ship this header file linked list.h. So looking at this header file, the user of our library will be able to know what are the operations that are available and the details of it. But the implementation of those operations will remain inside the binary library that we will ship. So that means this linked list.h is going to be exposed to the users of our data structure. So we don't want any data structure or any variable name that we are using internally which need not to be known to the user. So for those types or functions that are internal to us, we will have it in separate header file which we won't ship or which we won't supply to the users of our library. So this is the linked list impl.h file. For example, we will have this list head pointer as well as a function to create a node. Okay, so that's the idea. So let's go to the implementation of this linked list. What it does is, so we start from the top. It includes the header files. It also includes our header files. This header file gives the definition that of all the functions that we need to ship, and also this one is the internal header file. So create node is defined in ll linked list implementation.h file. Create node does what create node does basically is it receives the information integer information part of a node, and then it creates a node on the heap and puts that information into the info part of the node, and then sets its next pointer to null. So create node also checks if the list head is null. So remember, the list head is pointer to our special node which contains which is the first node of the list, head node of the list, and the information part contains the count of the nodes. So if it is null and somebody is creating node, we assume that we should have the list head allocated as well, because we always need to keep the data about the linked list in the list head. So if some node is getting created, we need to make sure the list head is up and ready to keep the count of the nodes and so on and so forth. So the create node function checks if the pointer is null, then it also allocates a list head node, and then it sets the default values, and then at the end it returns the node that it created and put this information in. So this is how create node works. Insert at front info. So it basically will insert a node in the front of the list. That basically means it will insert immediately after the list head. So it creates a node with this information, we get that node. Then the list head is pointing to the node, first node of the list. So now, because the new node is becoming the first node of the list, its next should point to the wherever list head is pointing to. List head is pointing to the first node. So the next of the new node points to the first node now after the execution of this line. And then list head should point to the current first node now, which we have created. So list head next is pointing to the new node, and then we need to increment the count in the list head info. So that is how it is inserted. A node is inserted in the front. Insert at the end, we have this information and we create the node with that information, and we start from list head and go until the end of the list, the count of the node we get from the list head information. And then at the end, we assign the last node's next pointer to this list, because last node's next pointer is null. So we set it to current node. So our last node becomes our new node. The new node basically becomes the last node of the list. And then we just increment the counter in our list head. So remember, the create node, when creating the node, sets the next pointer to the new node as null. So we don't need to set it again over here, because the next pointer must be null for the end of the list, the last node of the list. Insert after. So it inserts a node within this information after the node that has the information equal to after variable. So we do the same process. We create the node with this information, which is called P. Then we start from the first node in the list, which is pointed to by list head next. And then we go trying out to figure out where the information is there. Equal in the node, the information part is equal to the after variable. And if it is, we have found our node after which we need to insert the node. So we insert the node after that and increment the list and the count of the nodes. Insert before, similar thing. The only thing is we need to keep track of the previous node, and because we need to insert the node before the node that we find with this information. So therefore, it is equivalent to inserting the node after the previous node. So that's what we do over here. We keep track of the previous node and we insert the P node after the previous node, so which is effectively becomes before the before node. And then we have deleting the list, deleting the node from the list with this information. So first we check this information, where is that information lying, and then we delete the node by freeing the memory, and then we also reduce the number of the nodes from the list. And we make sure that we don't break the link. We just make sure the previous node points to the node after the node which is deleted, so that we don't lose the list. Delete list completely deletes the whole list. One by one it deletes, it goes to the pointer, it goes to the node, frees up that pointer, basically deleting the node. But before it frees up that pointer, it makes sure that list next points to the next node, so that we don't lose the um, pointer to the rest of the list. So it deletes the first node, but before it deletes the first node, it keeps make sure the list head is pointing to the second node. Then it frees up the second node, and again it comes back to the frees up the first node. Again it comes back to the second node. Before freeing it up, the list head next will point to the third node, and then it frees up the second node. Then it comes to the third node. Before it frees up third node, it makes sure the list head points to the fourth node. Then it frees up the third node, and so on and so forth. So we don't lose the remaining list as we free up the node. And once that is done, for all of the nodes, we free the head node and set it to null. So that completes our deletion of the list. Node count is simply implementation. If list head is null, it returns 0, otherwise it returns whatever information is there in the list head. And for ith node, nth node, it returns the information of this index at this particular index. So it basically iterates and goes to that particular node and returns the information. And finding node, again, it just starts from the first node, from the next pointer of list head, which is the first node, and until it matches the information, it just iterates and goes to the next node, and so on and so forth. And then if the p node which is pointed to by p is null, that means we did not find the node. So it simply returns boolean 0 or 1 depending upon the value of the p. If the node is found, the p pointer is pointing to that node, therefore it is not null. So therefore p not equals to null will return true or 1. So this is the implementation, pretty straightforward implementation of the linked list. So this I have already done, because the real part is going to come and come about after we are done with this experimenting and understanding how the simple linked list works. I have just put some data over here. So let's see and execute it and see how it works. So insert at the end 10, 11, 12, 13, 14, 15, and display the list. So if we go back to our console, it displays the nodes 10, 11, 12, 13, 14, 15, and 16. Then it tries to find the node 12, it finds it. So it will say that I found that node. Then it deletes the node with information 12, deletes the node with information 6, and display the list. So now we can see, take a look at the out the finding of the node 12. It was found. Now we delete node 12 and 16. So the list is not having those two nodes. And then um, we try to find that node. It is not found. So it is not found. And then we try to restore the list by inserting 12 before 13 and 16 after 15, and then we try to find the node. Now it is found, and we display the list. So we display the list, it is back to the same state it began with. Then we insert 9 in the front and we display that list. Now it starts with 9, and then we delete the list and we try to make sure that if there is nothing in the list, still we are able to insert in the front. So it should happen. So 92, 91, and 90. Now that we have seen a regular implementation of linked list, we'll go into little more details. Our current linked list implementation, if you see, is based on this structure of the node. It has got two in parts, the info part and the next pointer. The useful part for our clients, the users of our library, is this info part, and its type is declared to be an integer. What that means is that our clients will be able to store only integer types or information which is in integer or numbers form into the linked list that we have. That is very limiting. Actually, it puts a lot of restriction because the data could be anything that user wants to store. It could be a basic type called like a character or a float or a or set of strings, or it could be some complex structures also. For example, in our previous video related to dynamic memory management, we talked about reading data in structure student, and we were reading this data from this particular file, the ID of the students, the CGPA, and the name into a structure. What if we want to store, or our client wants to store this list in memory in a linked list? We surely cannot offer this plan or this linked list implementation to our client because the info part where that structure should be stored is actually of type integer. We cannot also predict what other structures or what other types our clients are going to store this um, into our linked list. So we cannot put a particular structure like student over here. All right, because we are in a library and we don't know, we cannot anticipate what all types of objects will be stored in our linked list. So what is the solution to that? That's what we are going to talk about. How we can make our implementation of the linked list into a more generic linked list that our clients can use to store any kind of objects. So let's go to that path. So we'll keep this current implementation as it is, okay, because we'll try to at least reuse some of the code, and we'll create a new header file in our project, and let's call our new implementation as generic linked list.h, just like on the lines of the arrangement that we have already in our regular or integer implementation of the linked list. We add a new header file. In this header file, we just do the similar interface that we provided for our older implementation. We just copy paste over here, but we make some changes. This structure will change into void star. For example, it could change into void star. If we keep this as our info part, void star can point to anything. It could also be, for example, union of um, things like basic data types, int, info, char, cinfo, float, finfo. We can have something like that, and then we can also put void star as vinfo. So the client could be free to implement what any kind of linked list. So because so though this is possible, but because void star is actually pointer to anything, it could be pointer to even basic types as well. So therefore we will just make it more straightforward and simpler. We'll just have void star as our info part. Okay. Now let's change it to node G, and let's change the type def of node G to G node. So G node is our type that we offer to our clients that they can use to store any kind of information in the linked list. for because we are putting it in the same code that where our current implementation of linked list is. So we'll just change the names of some of the functions so that we can distinguish it from the other ones. In more professional implementation, probably you will have this implementation as the default or the only one in your library. So then you can remove these special names of the functions and have regular interface functions. So insert at the front G and insert at the end, and let's change the function to G. For these functions, insert after and insert before, we will visit them little later. Uh, this also, the delete one also, and also the find node. We'll come back to this. So let's implement other functions first. Get node info. So node info for a particular index will return a void star, the information part of the node. Int node count, g node count, get g node info, delete list g, and that's pretty much is this. All right. So similar on the lines of some special or internal implementation that we had in linked list impl.h, we'll add another header file which will have internal implementation for generic linked list. So let's add that header file. So let's name it to generic linked list impl.h and copy whatever we have got here to here, and we actually should have standard lib.h here so that we get this null definition. List head g, create g node, node becomes g node, this node becomes g node. Okay, so this is our internal header file that we are going to use. Now let's add the implementation file. C++ file, and so let's name it generic linked list.c. Add this file. Here we'll implement the interface of our linked list. Okay, and we need to include here generic linked list.h and generic links. No, we just need to copy it here. Okay, and the header files. We need to include our own header files as well. We don't need to include this because impl header file already includes the general header file that we want to ship along with our library. So this will be void star. Let's fix that in our header file as well. So one good thing is that the algorithm will remain pretty much same. So we will just be able to get the implementation from our older implementation of linked list with the info part as integer. We just copy it and do the necessary changes. So we'll quickly do that. G node, node becomes G node everywhere, and list head becomes list head G, and G node becomes G node. That's pretty much it. Also, we have the next function. Let's hope this guy gets it to be inserted in our existing file. No, not yet. So just copy it for now. And get the definition of insert after G. Insert at front. Sorry, it's insert at front. Node becomes G node, and create node becomes create node G node. List head becomes list head G, and we need to typecast info of head node into integer. So what are we doing here is the head node also will have info part as void star, but we are storing counts in it. So we need to use that void star variable as an integer. So therefore we need to cast it to integer wherever integer specific operations are there. For example, this plus plus and minus minus would come in deletion of the node. Then the next function is insert at end. Let's see if it gets now that we want to implement in G. Yeah, it's getting there. Control S, delete list as well. Control S, and get G node count. Control S, and get G node info. Let's implement these functions. Insert at end, insert at end, here it is. Node becomes G node, and list head becomes list head G, and we need to typecast the information part of list head into an integer before incrementing it. That's pretty much it. What about the delete list function? Copy the code, and control S, node becomes G node, and list head becomes list head G. Okay, so we'll come back to freeing of the memory later, but for now let's keep it like this. Then we return list head g equals to null. If it is true, return 0, otherwise return list head g um, info part, which will be the count, and get node info given an index. We'll take the code from this place, copy here, and again change node to g node, list head to list head g, and we're done. Now let's add the client side code which is going to use this list. Let's open, create a .c file, generic list linked list use, and we include the generic linked list.h, and we just move the main method over there, so we just rename it to something and close this file. Void main, we insert at end 10 or 20, just to be different from our regular linked list data. Insert at end 30, 21, and 22, 23. Okay, and then we'll implement one function, display list, that we already have here in the source.c, display list. Display list g, and g node count, get g node info, and we print it, display list g. All right, so now we are done with the implementation of this generic linked list. Let's, and we are ready with the client code as well. We are going to use it. Let's run it and build it first. If there are no errors, we'll run it. Okay, going inside insert at g. Now we are in our library code. It is going to create a node. Okay, so we just need to change the function call to our generic function, not create node. It should be create g node, and this also should be create g node. That is done. Okay, let's run it again. Insert at end, create g node. It is creating a node, putting the information there, setting null, setting up the head node with the count as 0, next as null, and then making sure we are setting it up and increasing the pointer variable to as a counter to 1. You can see over here the next list head g is 1 now. So we go back, we insert other things, and we display the list. As we can see, we are able to see the list. So this is the implementation equivalent All right, so let's move to a little more sophisticated scenario. We want to store this data in this file into a linked list after reading it into student structure. Remember in the dynamic memory management exercise in that video, we used this file and we also created the student structure. So we'll try to just take some code from there and let's we already have a student.h file in this project and we just need a similar type def like we had in our dynamic memory exercise. Name of the student, id of the student, and the cgpa to store the cgpa values. Let's add its implementation over here. Student.c file. Remove we'll just change this main file, move the main function to that file, student.c. So here we just rename it to some other function. In student.c we include standard lib.h, include standard io.h, and the header file for our linked list implementation. Then we have our main function over here. Now we open the file and read the data into that structure so we can reuse the code that we had in our dynamic memory management exercise. Here it is. So we just copy this code from here, we read the file, and we get this code, display student data. Don't need the whole code though. Let's copy it and paste it over here. We don't need student count because we are storing the count of the nodes in the head node. We remove this. We don't need this allocation because we will use our linked list structure to allocate the nodes for us. Surely we need to use this get student data to read the data. All right, so we include the student header file, get this function from the same code. We kind of keep the code for this function pretty much same because we just allocate and fill up the structure. So we um, also implement display student data, so that will get the data of the student from the node directly. So we don't need it here, we just get the count, gnode count, how many student nodes we have, and then we for every gnode we get student star ps equals student star get gnode info. For every node, get gnode info returns void star, so we convert it into our pointer and then we use this pointer here. Control H with PS. That should take care of it. At the end we just print f small separator so that we can know where one list is ending. That's it. Now coming back to the main function, we don't need this array, we also don't need this allocation, and we just need a call to this function. After, if the student is not null, after we get the data from the file and it is not null, we insert it into the insert at end g and pass this pointer. That's it. Okay. Let's compile it. There seems to be some compilation errors. Let's see what are they. Student.c. Display students data. That should not happen. And what is this error? PS is undefined. Okay, so this is the issue. Okay, so we build it. All right, so now we are able to set up the code that will use our linked list in to store in the nodes info part our student structure. So let's see how it goes. Let's run it. All right, so we read the file, we get the data. So we can see first data coming in, it's not null. We insert at the end, create the node and do the stuff, insert at the end, and we again insert till the student structure is returned as null. And now I guess it is null. Break, display student data. Let's check the output. So now we can see our linked list is containing the data in form of student structures. The nodes info part is pointing to the student structure. Okay, so that's good. At this point, we should see what is the memory picture looks like. In our case, in our linked list thing, we have this student structure, and let's see how it looks like. So we have pointed to the linked list. Here it is. So this is how our node is created. So this is our linked list node, and this is the info pointer. This info pointer is pointing to a student structure this guy is having pointer to name of the student. So remember, this whole thing is part of heap memory. It is on the heap. It's all heap. So this node's next pointer is pointing to another node whose info part is again pointing to the second student structure, whose name is again pointing to some location in the memory, and so on till we get to the end of the list. This is how our memory um, picture looks like. So on the stack side, we have list head G. List head G variable is pointing to the first node of the linked list. So this is how our memory picture looks like at this point of time. Okay, so why I'm showing you this is that now we have reached to the stage where we want to see how memory management happens. How do we need to free the nodes and other things. Okay, all right, so let's go back to the definition of our interface. Remember, we left out some of the functions. Now let's enable them. Insert after, insert before, delete, and then find node. Insert after will take a void star and void star comparison for the comparison part, void star and void star for the comparison part again for this function as well. Let's change their names as well. Delete G, delete the information, the node with this void star information, and then find G node, find a node with this void star information. Okay, and let's insert the definitions. And let's fill up their implementation. Insert after G. So what did our original implementation look like? We'll go to that. Insert after. Let's copy this code and paste it into this function because the logic remains same. G node becomes G node. List head becomes list head G. And we need to typecast this into an integer. Okay, now here comes the interesting part. In this implementation of insert after G function, what we need to do is we need to compare the information that is there in the node with the information in this variable so that we can make a decision whether we have found the node after which we need to insert the new node. Now remember, in our previous implementation, this info part was an integer. The after variable was also an integer. So there is a direct comparison check between these two things. Integer is compared to integer. But in our current implementation, it's a void star. Now we don't want to compare the values of the pointers. The pointer variables are storing addresses. We don't want to compare those addresses. When we have void stars, this check is comparing only the addresses part. What we need to compare actually is the values that are pointed to by these void pointers. Now, how do we do that? Remember, we are inside our library. We are trying to implement the interface which is going to be used by the client. We have provided the flexibility to our client to store any kind of data in our linked list using the void star pointer. So that could be an integer, that could be some structure like the student structure in our case, but it could be something else as well. So the basic point is that sitting inside the library function, we have no idea what kind of objects our linked list is pointing to. All we know about is it is pointing to a node, pointing to a memory location. We have no idea of the type of the node, info part of the node. So therefore, sitting inside library function, we do not know how to compare those info parts. We don't know how to compare, or we do not know how to compare the values inside the structure of student. Out of three values, which value we should compare, right? So how do we resolve this issue? So the solution is very elegant and solution is very powerful. Remember, this is the generic header file that we will ship with the library implementation to the client. For example, um, in the previous in the client implementation here, the client will include this .h file. So what we do over here is, in addition to having a type def g node and the node structure, we put a function pointer which returns an integer, a comparer function pointer which returns an integer and takes two void star objects, object 1, object 2. Now what we do is we can mention in our release notes or as a comment over here what we are expecting this function to do. What we expect this function to do is to compare the object 1 and object 2, and just like string comparison functions, it should return 0 if the object 1 and object 2 are same or equal. Otherwise it should return 1 if object 1 is greater than object 2, and -1 if object 2 is greater than object 1. Okay, just like string comparison function. Now we declare it here in this header file, which is visible to the client. So when the client comes into picture here, they include this header file, and then they see this, that there is a comparer function that we need to supply. So they implement this function of comparing two objects. So int student comparer void star ob1 void star ob2. So its signature is matching to the function pointer that our library has. So it first typecasts the objects because it knows the data type is student star. Actual object is of type student. So it typecasts those objects into the correct pointers before using them. S2 equals to student star. Okay, and after that it just uses string comparison of S1's name and S2's name and return whatever string comparison returns. Now, before it starts using it in our library calling in our main function, we will set this comparer to point to student comparer. What are we doing over here really is that we are providing the library a function implementation through the function pointer. This is very powerful concept. Let's now go back to our implementation over here. So here, instead of comparing directly the info part and after part, we call the function attached to this function pointer using the function pointer variable and pass on the two objects we want our clients to compare and return check if it returns 0 and then we will see. And we now execute this function and let's see how it goes. Now here is where we are assigning the student comparer function, reading the file, reading the student data and insert at end. Okay, so we just need to first call the insert at the front insert after function after we display the data. Let's create a new student object. Student star ps equals to student star malloc size of student. So what I am planning to do is we already have read the data. When we reach over here from the file, we'll just insert a student object at the end of some one particular student. Okay, so we put the data here, ps id, some id we give 9, ps cgpa and ps name some Harry store, whatever the name is, and let's say we want to insert it after Hastings Baker. So it is third student, so index will be 2. What we do is we get this information from our insert after equals to get gnode info, index is 2, and we just converted. Student star, and what we say is that insert after G, we want to insert our new student PS, insert after P, insert after, and then again display the student's data. All right, so let's run it. So if we see the output here after the second student, so here is the first student, the second student, and the third one Astin, which is index 2. We have got Harry Star in our new list, which was not present in here in our older list. So we can see that we are able to successfully insert the data into the file, into the linked list using insert after functionality. This comparison, um, just a second, I'll just add one new line character over here. And just to make it more clear, we'll run it once more. Now it is good. So we have our initial list of the students, and then in the next list at line position number 4, which is index 3, which is after index 2, which is Astin Baker, we are able to insert Harry Star, the new student that we created. So this is how we are able to create the add the new object inside the list after providing the student comparer function. This is very important and very powerful concept that we have talked about, that we have been introduced to today, using function pointers to let client execute some of the rationale that are useful inside the library. So see, this is what is happening over here. When we are inside the library, we are sending the callback back to the client, to the function that client provided us, so that we can complete the comparison in this case, and then the result of that comparison, which is done inside the client code, comes back into the library code, and we use that result to move ahead in our algorithm. This is a very strong, powerful concept. It is called callback mechanism, and it is very, very important to learn it. Okay. Now let's complete rest of the functions. So we have completed this insert after G. Similarly, insert before G. Insert before will have similar implementation that we had in our older list. Let's copy the code, and then we need to do the changes as usual. Node becomes list head becomes list heads G. Node becomes G node, and we need to typecast info part into integer before incrementing it. Similarly, we need to get to the delete node. node becomes G node, list head becomes list head G, and we need to typecast the info part into integer first before decrementing it. Now let's talk about, okay, so once before that we want to fix the comparison parts. So here also there is an equal to sign, so we just use the comparer and pass on these two objects to that client function and see that if it returns 0 we break. Similarly here also we have comparison, so we use comparer function and again we break here. In delete list also list, okay, so we're done with this. Now let's come to the freeing up of the memory part. Now delete G. So if we take a look back into our diagram of our linked list, so here the nodes are implemented inside the heap. So this is heap memory. The nodes are implemented inside the heap, and we need to free, when we delete a node, we need to free it up as well as the object that is pointed to by the node. So surely the node has pointed to the student object. So node has pointed to the student object, but sitting inside the linked list implementation, we only have that pointer to the object. We do not know whether that object which is pointed to by our info void star pointer is further having any memory allocated to its properties. For example, in this case, the student object has value name, pointer name, which is, or property name, which is again allocated memory on the heap. Okay, so now we need to, if we want to free this node, we need to actually also free the object that is pointing to the info star, but also we need to free up the memory that is that is occupied by the name of the name property of the student object. So let's do that. Sitting inside the library, we do not know whether there is any property that is pointed to by the info part of the node into the heap memory. So therefore, we do not know whether how to free that memory. We do not know how to free the memory captured or allocated by the properties of the particular object. So therefore, we go back to our function pointer solution. Instead of we guessing and trying to release whatever properties are allocated memory on the heap for the object in the node, what we do is, again, we provide a function pointer to let the client of the of our list free that memory pointer to by the object properties. So free object props memory. So what we expect our clients to do is provide us a function which we will call before we call a free on the object which is pointed to by info pointer, which that basically means the student object in our case. This student object in our case. So we'll give a, before we delete this uh, node object, we need to delete the student object. That we will do from inside our linked list implementation. But we will, before we do that, we'll provide a chance to the client of our list to free up memory allocated to the name property of the student object. So that is how it goes. Remember, in our dynamic memory allocation exercise also, we first had to delete the name object, then the student object, and then the pointer that were holding the student object. So this is the same scenario here. We need to first delete the name object, then the student object, and then we delete the node object, which is holding up the pointer to the student object. But this name object, we don't know whether it exists or not, sitting inside the client, inside the library implementation. So but our client knows, because the object is owned by that client. So we provide a mechanism to our client, a chance to our client to free that memory up. So let's see it in action now. So we provide this function pointer. Our client sees that here in the linked list header file, it sees that there is a function which is available for us to free that memory. So it implements free name pointer, and it simply, okay, so it needs to get the pointer to the object for which it is going to ask for us. So we need to just change the signature. So white star object. First we cast it into student star. Do we want to delete it? And then we say free del name. That's all we need to do in our case. And we just set this to free object props memory equals to free student free name pointer, and we just update the signature of this to pass it white star object. And when we go to our implementation of delete node, now here, if we get the delete node to free, so first we ask the client to free the memory. So we use the free function pointer and pass it p info. Now we are passing it the pointer to student object for whom we want to free the memory. And then after the call, this call will free the name part. We are going to free the object pointed to by info, which is the student object. And finally, we will free the node, which is pointed to by p. One thing, it may not happen that it may happen that the structure or the object that we are storing in our linked list is not having any property who has got memory allocated on heap. So therefore, this client may not provide this function. If it is null, then we don't call it. So we call the function only if this function pointer is set, and we free the list. So this is very important to understand. And again, we are using this powerful concept of callback functions to properly free up memory for before we delete the node that we have. Okay. Again, in this case, we are freeing up the memory. So here also we will implement the same thing. For deleting the whole list also, we just need to implement the same functionality. We are deleting in this for loop every node, and at the end we are deleting the head node. Okay, so if it is not equal to null, we ask our clients to free the memory allocated to properties of the object. We pass the information, we pass the void star pointer to that object. After that, we free the info pointer, the student object, and then we finally free the node, and at the end we free the list head node. In the head node, this void star pointer is not pointing to any object. It is just keeping the count of the nodes in that void star pointer. So basically now we are we have done our implementation completely cleanly. We have taken care of the memory management as well, and we'll just test it out shortly now for some scenario. So we have inserted a student over here, and let's say we want to delete Saner Pike. Let's say we want to delete Saner Pike, who's at index number 0, 1, 2, 3, and 4. 4, index number 4. So we say delete G, and we say get node info at the student at index number 4. Okay, so index number 4, 0, okay, so there becomes, it should be 4, and then we again display student data and we run it. Let's run it to this point. um, Run to cursor. So you can see we have this status where we had our original list, then we inserted Harry star here after Aston, and now we want to delete Saner Pike. Okay, so it it will delete the fourth index students, which is Bilas part, because we inserted a new one after our original list. So we'll delete the fourth index student, which is the fifth in the row, Bilas Bart. So let's go inside the function. So it is getting that node information. Let's go out of it. Let's go inside the delete G function. So we can see the info part is there, and we go to the comparer. So we can see there are two students. The object 2 will have the name as Bilas Bart, which is the student we want to delete, and we were comparing what is the name of the student in that node. If the node matches, we'll delete that node. So this is the first node, which is Shelly Boris, so that we don't return 0 for that because the name doesn't match. So we go on like this, and we should stop and break at the fourth index, which is now I equals 4. The name matches, so we make sure that we have the pointer to the remainder of the list, and then we see that the function pointer is not null, So we go inside that function, it goes back to the client code. Now we are inside the client code. We get the student object and we free the memory for the name. So you can see that this name is gone here. Then we come back into the library code. We free the object and we free the node, and then we remove the we reduce the counter by 1. So that basically deletes the student, and then we display the data. So here we see there is no Bilas Swart in the new list. After Harry, there is Saner Pike. Bilas Swart node is gone. And we have deleted this node cleanly. We did not leak any memory. We used the powerful concept that we learned today of function pointers to be used as callback functions, and we give chance to our client to free up the memory that they allocated in the properties of the object, which is pointed to by info pointer of our node. And this is how we can implement a generic linked list with proper memory management. Okay, so this clears up, this completes the beyond Hello World linked list implementation that I was talking about. And I hope you guys found it interesting. And I will highly recommend that you do it hands-on using the code that you see over here. You should do it on your own. Once you're able to do, you can think of you know, any scenarios like student in structure. In our case, you can take up players, for example, or any other structure and use the similar exercise. And once you do that, I'm sure you will feel confident about the concept at large. All right, then, good luck. Have a good day. Bye bye.